Hello everyone. Today I will be solving one of the questions from my assignment from last week. So the question that I will be solving is the question number 3, which talks about finding the minima of the function f, which is subjected to a constraint equation g. So the theme of the question is related to Lagrange multiplier method. So we will talk a little bit about it, and let's dive in. So we use Lagrange multiplier method whenever we want to find the point of local minima or maxima of curve which is subjected to constraint, and this approach is very helpful in finding the local maxima and minimas of these curves. So here you can see in this graph, I've tried to represent this question graphically, where this curve have multiple level curves, as you can see pointed in the graph. So supposedly we have a curve for which we want to find the local extrema, and it is also subjected to a constraint equation. So one of these level curves would just touch the level curve of the constraint equation, or the curve that is given to us, and that point where it touches both the curves, we would have a common tangent. This point would give us our local extrema. So here also you can see that we have these f curves that are given to us, and this is a constrained circle equation that is given to us. So one of the contours of this f curve, or one of the level curves of this function, just touches the constraint equation, and this point where it touches, this point would give us our local extrema. So how to find out the point? We need to see a little more about it. So here in this diagram or graph, you can see that the gradients of the constraint equation and the function are normal to the tangent and are in the same direction. So this implies that they are scalar product of each other. So using this logic, we will try to find out the point of local minima for the question that is given to us. So let's just solve the question now. So in the question, we are given that we want to find the minima for the multivariate function which is constrained by function g. These are the equations of the functions, and we will use the Lagrange multiplier method that we just discussed about in this question. So according to the Lagrange multiplier method, we talked that the gradients of both the function and the constraint curve would be scalar product. So here we are using that logic here, and the partial derivative of function with x is a scalar product of partial derivative of g with x. Similarly for the other directions as well. So we'll solve each one individually, and we will try to find out the value of lambda here. So when we solve one, we will take the partial derivative of f with x and partial derivative of g with x, and we will find we get a value of lambda as 2 by 3x. Similarly, when we solve for the lambda in the second part, we will get the value of lambda as 4y, and similarly in the third, when we solve, we will get the lambda value as z by t. So when we equate these equations, we will get a relation between x, y, and z. So once we get this equation, once we get the relation, we will just substitute these values back into our constraint equation. So first we will solve for x, and once we substitute these values in x, we will get the value of x is 6. Similarly for y, we will substitute the relation that we got for lambda here, and we'll get the value of y equals to 1. And for similarly z we will do, and the solution for z is 8. So the point of local extrema for the function f with the constraint of function g is 6, 1, 8. So this is the solution of the problem. Thank you so much.